everybody. Welcome again. It's great to see our regulars here. So welcome to the third in our series for our Spring 2024 Science for Communities. And so again, this is our third one today. You're going to hear all about our new ACEs initiative that Dr. Andrew Hayes and Dr. Michael Gonsior are going to present on. And next week is our final in our series. And Dr. Chris Rao here will be talking about biodiversity in the human era. So same time, same place next week. And just, I know you've seen this before, the dolphins are back. And so we've had our first sighting. So for those of you that are on the Dolphin app, you've probably had an update recently. And for those of you who don't have the app, please take the leaflets at the back of the room and outside in the foyer. This project is just, it only happens because of people like you. And so you're out on the water, go click that you've seen a dolphin and send us an image. But they're back already. So this evening, you're going to hear about one of our new initiatives here at the Chesapeake Biological Laboratory. It's the Anthropogenic Changes in Estuarine Systems, or ACEs for short. And it's headed up by Dr. Michael Gonsior and Dr. Andrew Hayes. And this was thanks to a $1 million gift from Brian Hockheimer and Marjorie Wax to initiate this. And it's bringing in state-of-the-art analytical equipment to allow a number of our chemists, including Andrew Hayes, Michael Gonsior, and also one of our new employees here at CBL, Stephanie Landerwehr, who is a postdoc here in my laboratory. And what everybody is involved in is studying emerging contaminants. I'm sure you've all heard the news all about a number of contaminants that are impacting either ecosystems or humans, things like sunscreens or PFAS. You know, every day you hear a new chemical that the media is talking about. So we have a 100-year history here of studying chemicals and water quality here at the Chesapeake Biological Lab. Our peer has been monitoring water quality for nearly 100 years now. Again, next year is our 100-year anniversary, so stay tuned for some really great events. But it's the data like that that's been extremely important. You see, as you drove past our Solomon's climate sign, that is the actual data, water temperature data over the last 100 years. And that is showing you how our water temperature has changed over the decades. And then some of that data has also been very instrumental in terms of management and policy decisions here in the Chesapeake Bay, in terms of nutrient management, and all sorts of other policy decisions in terms of water quality and the health of the bay. And we have been a sort of a global focus on this that many other countries have also looked to learn from some of the things that have been happening right here in the Patuxent River and the Chesapeake Bay. So I'd like to introduce our two speakers for this evening. Dr. Michael Gonsior is a professor here, right there in the front row. He's an analytical chemist, a marine biogeochemist, and he does a lot of things. One of them is looking at the molecular diversity of complex dissolved organic material, looking at the optical properties of these, photochemistry, and then looking at high molecular weight disinfection byproducts, and a number of other contaminants, including sunscreens, PFAS, and the like. And then second, Dr. Andrew Hayes is an associate research professor here. He's also an analytical chemist, trace metal biogeochemist, and works also with a lot of different organic contaminants. So his area of expertise is actually called on very recently with the Key Bridge collapse and the issues of you know, what are the dredge materials, the contaminants, contaminated sediments. He's been working up in that area, I wouldn't say decades, sorry to age you, but his lab has done a lot of analyses in terms of assessing sediments for inorganic contaminants like mercury and metals, and also inorganic organic contaminants like the PCBs and the PAHs. So both of our analytical chemists do a lot of really important work looking at historic, current, and emerging pollutants here in the Chesapeake Bay. So with that, I will pass it over to you all, but let me set this up. Okay, that should be it. So over to Michael and Andrew. Thank you.
Okay, so we're going to give this talk in two sections. One, we're going to try to talk a little bit about the background and how we got to where we are and why we want to do what we want to do now that we have the capability, or we're getting the capability going. So we'll go through a little bit of the what, why, a little bit of the background on the Chesapeake Bay, some of the issues, and then we'll turn to the Patuxent River, which is something that the CBL has studied for a long, long time. So our mission, we are scientists at CBL who do work all over the world. And one of the things we try to do is bring this experience that we get from studying other ecosystems, as well as studying the Chesapeake Bay, and bring those together to solve some of the local problems. And we've done that with Calvert County, with Charles County, with other counties, Anne Arundel County, and the state government, of course, in many, many instances. So waterways around the world are under pressure from human activities. One of the things that's happening is this migration of population to the coast, to the Great Lakes areas, to areas where there's water. Water is really important to us for industry, for drinking, for agriculture, and so on. But it's interesting to look at the population migrations around the world and these concentrations. And of course, the climate is changing, right? So of course, we're moving to the coastal sites, and of course, we're getting more storms. The temperature's going up, water temperatures are going up, and we're getting more rain events. We're getting stronger storms. And what are the implications of that with all these people now up against the coast? So the Chesapeake Bay is under a lot of pressure. We've known, and you've seen it in the news for decades now, agricultural runoff, nutrients coming from homeowners, from just development in general. Pesticides, antibiotics used in agriculture and stuff are all coming down, ending up in the Chesapeake Bay. We've got a lot of industry on the bay. We have a lot of shipping. Shipping is increasing. We use things like anti-fouling paints. We coat the holes so that things don't grow on them. Even all your boats around here have copper kind of embedded in the paint and so on. We have metals and microplastics all out there now. Then we have industry. There's a legacy of contaminants from Port of Baltimore, from the heavy industry around that. We've got things like Aberdeen Proving Grounds. We've got the base across the way here. So there's lots of areas where we've had contaminants come into the system, especially 100 years ago, fairly uncontrolled. And that has led to contamination of sediments. And of course, we have to dredge because our ships are getting bigger. And that creates other questions and problems that we have. Human waste, wastewater treatment plants. We've got a lot of those around. Population keeps growing. Septic systems, something we've worked on more recently. They're all over the place. In fact, septic systems is the most common way to treat waste around the world. It's not wastewater treatment plants. So some form of a septic system, some fairly primitive around the world, are really important to limiting the nutrient flow and other compounds that we use into our waterways. And then, of course, the climate change I mentioned earlier. We've got increased runoff from these rain events. I don't know if you noticed, but boy, those rain events are hard and fast. And then we have the rising water. We have saltwater intrusion, particularly on the eastern shore. In some of the counties there, it's becoming very problematic. And when that happens, then you've got this water coming up through the soil, and we're actually saturating the soil. We're getting more erosion. And one of the things that people don't really think about is that, well, that then leads to more runoff from all these other things that we put on, the nutrients and the pesticides. But we put some of our waste on those fields as well. You know, we take our waste from the anaerobic digesters and we spread those on the firm fields. So that's another way for contaminants that may not break down to get back out into our waterways. So today's menu, I'm going to spend a little bit of time talking about some of the legacy, our past, you know, how important are these pollutants right now. Then we're going to move into the watershed, and we're going to look at the Patuxent River, and we're going to look at some of the sources there, what, where, when, just how important they are. Because some of these contaminants that are being released, we call them contaminants because they're not natural, but they may not be that important. That's one of the things that we have to do is triage it, if you like, to find out what are the problems. Who are the problem children? And then moving forward, these contaminants of emerging concern. We've only really developed techniques to measure them, a lot of them recently. So again, just because you can measure it and detect it, as Karis always says, doesn't mean that it's actually a problem, because the concentration could be really, really tiny. But so again, we have to figure out which ones are important, the toxicology and so on. But we're really only just starting to get the techniques going to measure many of these contaminants. So legacy. Many industries have resulted in contamination of sediments and estuaries. This is global. I mean, we put a lot of our industry right on the ocean, in estuaries and rivers where we can get access to shipping and stuff. So heavy things coming and going, we need water for production. And naturally, especially going back 100 years, there wasn't really much concern about what happened to the runoff from those sites. And sediment was being eroded, and all the contaminants which are released into the rivers. The most commonly mentioned ones are PCBs, polychlorinated biphenyls and polyaromatic hydrocarbons. We hear about those all the time, oil-derived products. And then metals, so things like zinc and copper, lead and stuff that we've used in heavy industry. But then there are many organic compounds that were used over time that we don't really know much about. They were used for cleaning, for scrubbing, perhaps. They were used in paint mixtures and so on. And we really don't have a good handle on how to measure those. They were released into the environment many years ago. Some of them have broken down and changed, and they're out there, but we don't really know much about them. But the new flagship, which you've heard about, which is going to be our next legacy contaminant, is PFAS, right? I mean, again, something we've been using now for probably 50 years. And these compounds are forever compounds, right? So they're staying around. And again, we've only really recently been able to measure them in the environment. And there are hundreds, if not thousands, of these compounds. So we're only being able to focus on, I think, 40 right now is the number. So there's a lot of work to be done. Again, figuring out which ones are important, what concentration levels are important, and so on. I always like to show this picture because it kind of shows change. This is Baltimore Harbor. This is a long time ago. You know, and I kind of look at that picture and I go, you know, that could be Solomon's Harbor, right? I mean, it's just some houses around, some ships coming in. There's not really much industry or anything like that around. And it's very nice and quaint. And then you look at a picture, you know, 50 years ago, and it doesn't look anything like that, right? I mean, there's a lot of heavy industry, which pumped a lot of metals and organic compounds into those sediments in a very localized way. So they're really focused in the harbor. The way the circulation is, a lot of those sediments are trapped. Now we've had new sediment come in and basically coat that area to a large extent. Some areas less than others because of the way the circulation is. So we have a little bit of a protected layer, a little bit. Because you see profiles like this, where you can actually go around the harbor and you can take cores, deep cores, and you can date the cores, and then you can look at the stratigraphy and you can figure out what industry was going on at that particular time in that particular location. And you'll see big peaks, like what you see here, where there was some paint manufacturing, we had some iron ore production, and then it went away for a while. And then if you go into another part of the harbor, you'll find where they were building the Liberty ships, and you'll see, again, metals associated with ship construction. So, and these are pockets all around the harbor. So you can see that kind of work. So there's nothing to say that if you went out into Solomon's Harbor, that you could take a core in a few places, and you could probably find out where they were scrubbing the sides of the ship hulls, where the copper was coming off, for instance. So you could probably see that. But we've had a couple of incidents in the last few years, which are kind of, you know, make us rethink a little bit about our legacy contaminants. And we've had a lot of communication with the state and federal government over the last 2 or 3 weeks. And things aren't too bad. So the first one was the Evergreen ship that ran aground out here when it was coming down the Chesapeake Bay and kind of wandered off and kind of got stuck in the mud. It was in an area where the sediments are not that contaminated, but again, it had to be dragged off. There was a lot of disturbance. There were a lot of questions about what was going on with that resuspension. And then, of course, we have the bridge collapse. Again, the ship went off course a little bit there, took out the bridge, got stuck in the mud. And again, we have an issue where we have some resuspension. Luckily, it's not far off. There won't be much dredging. And any dredge material that is taken, well, it has to go to repositories within the harbor by law. So that's what's going on with that. But it makes you wonder, with all this new ship activity, and thinking about what can we do? You know, what things should we be actually thinking about? So these are Chesapeake Bay-wide issues. These are global issues. So again, now we're going to go local and we're going to take our local learning and we're going to take it global. Accidents. There's going to be a new bridge construction. So we have to think about that now. We're going to probably build a bridge very differently than we built the bridge last time. Dredging for transportation is going to be a common thing in many of these harbors. You know, we got all this erosion, constant sediment supply. I mean, they just opened up 9 gates up there on the Susquehanna River and the waters comes roaring down, right? Bringing in all that new sediment. So of course it's going to be dredging. Ships keep getting bigger. And then we've got the climate change component. Well, rising seas, well, that's not so bad, right? You get more left, you got, the water's deeper now. So, okay, but you've got a lot more coastal erosion. And there's a lot of that nasty material is actually still caught up in the sediments in the near shore zones and stuff. So we still have PCBs flowing in from point sources around the Chesapeake Bay. And if you bring the sea level rise up and you start eroding that, you're going to bring that new material in. So there are things we have to think about and we have to understand and we have to be prepared. And we are starting to think about it. So the Patuxent River is our laboratory for our new endeavor. CBL has been looking at the Patuxent River for many, many years. It's an interesting landscape. It's kind of an interesting mosaic of agriculture, some urban sprawl, and quite a bit of forest area, surprisingly enough. So you don't think so much about some of the new environmental challenges which are coming forward in such an environment. But when you look around the Patuxent River, you see a few things. You see the harbors like Solomon's Harbor in the middle. We have power plants. We have a lot of what I call light industry and commercial. So you've got a lot of paved road areas and you've got a lot of things like auto body shops. We've got a lot of things that are in our garages. We've got light plastics, light machining things scattered all over the place. And then we've got a lot of urban development. And urban development is different in different places. Like, you know, we've got pockets now around Prince Frederick and Dunkirk and stuff. And then when you get up further up river, you see things are quite different. But then we've got a lot of this sort of spread out housing with septic systems, and that creates another different environment. So this is what that looks like. So you've got this is a map showing different land use areas, and you've got some agriculture in the very northern end of the Patuxent watershed. Then the orange area is that nice big urban sprawl. So there's a lot of paved area there. And then you come down to where we live and you get that more mix, right? You've got the green, it's the forested areas. We've got some pockets of agriculture and then little pockets of urban development. So it's an interesting collage. And that's how a lot of the streams and the river networks around the Chesapeake Bay look like. Also, what we have are a lot of wastewater treatment plants. And that's something that people don't really think very much about. And what you see, the blue dots, are all the wastewater treatment plants. And where's the biggest density? Well, that's where the people are. But there's basically 2 types of wastewater treatment plants. There's these larger municipal ones, which are highly regulated and monitored. And then we have some small wastewater treatment plants with limited flow and limited capacity, and they are not so well regulated. And we really don't know so much about how they perform. And then, of course, when you get further south and you get into the lower parts of Calvert County and St. Mary's County and stuff, you don't see any wastewater treatment plants. So we're into septic land. So that's the predominant way of wastewater treatment down here. Runoff. A lot of runoff is where we get a lot of our pollutants being driven, both from the urban, the rural, and the agricultural settings. That delivers our nutrients. So from our yards, metals and stuff coming off roads. I mean, when we drive our cars and we hit our brakes, we put a little bit of metals onto the road, right? There's a little bit of friction there. You know, the brakes wear out, go somewhere. We've got catalytic converters, oil-related products, things leak and drip. Tire compounds. Tire compounds is a new one. It's very interesting and very hot on the EPA radar screen now. And tire compounds are interesting because our tires wear away. The rubber quotes, goes away. There ain't a whole lot of rubber in a tire anymore. So sources, this goes back to 2007, and I found this kind of interesting. This shows you the sources of nitrogen and phosphorus to the Patuxent River. And you can see urban is actually the largest source. of both phosphorus and nitrogen, which is kind of interesting. Agriculture. You think about that watershed, that diagram though, there's only a little bit of agriculture in the top and little pockets everywhere. So the urban is the biggest component. You have some point sources, septic tanks. Some of these numbers are probably not the best, but it gives us some indication of what the distribution looks like. So what happens when it rains? This is a picture of a hydrograph. What you have on the one axis over here is the flow. So this is the flow and the dots here going up. And the metals typically peak following the hydrograph. So this is rain starts, runoff starts, metals come out, and then there's a flush, right? And these are two different hydrographs show the same thing, flow, metals peak, and then they subside. So we get a nice flush of metals into the system. This is mercury. This is my favorite metal. And mercury behaves in a little bit different way because what you have here again is the hydrograph in the solid line here. Now what you see here is this is the particulate flux of mercury coming off the surface, and this is the dissolved flux. So most of the mercury is associated with particles. So it's true of many of the metals, even the break dust and stuff, a lot of it is associated with particles. So that's one thing that we're somewhat interested in as far as trapping metals and stopping them from going out into the environment. Oil is a little bit different. You notice when the most dangerous time to drive is right after it starts raining because it gets really slick. And that's what you see right there. That's the PAHs, that's a big pulse. This is a measure of the organics. So it starts raining early in the hydrograph in this particular case, and the organics are already liberated off the surface and running out. So that's kind of an interesting thing to look at, and then the hydrograph follows along and the concentrations go way down. So there are ways for us to mitigate this, and this is what we're starting to look at with the counties and the state. Keith Ashelman, our colleague up at Appalachian Lab, has been working on swales, looking at metals in different parts of the state. So there are different ways to trap a lot of our runoff. Retention ponds, you'll see these all over the place, especially in some of the new around parking lots and stuff and the new industrial developments. We have roadside trapments here, like where the water will come off into rocky areas underneath here, or sand areas, again, to trap the particles. Really, they're put in to slow the water down. They're not designed to trap the particles, but what we're looking for is a added benefit, is what we call it. And then there are these tiered like developments like this, where the water then will drop down and cascade and again, slow the water flow. And hopefully you'll get particles dropping out over time. One of the problems with some of these things is we don't know how long they last. We haven't really monitored them for contaminants. We don't know if there's an added benefit. People think there might be, but there's been very little done, and that's where we're going to come in. These retention ponds, many years ago, I had a meeting with Virginia and Maryland, and one of the things we were concerned about is that these things eventually fill up. Like the sediment keeps going in, there's no drain there. So eventually your retention pond fills in. So when your retention pond fills in, then you've got sediment that has to go somewhere. And one of the discussions was, is it now contaminated? What else is in there? And is anyone really looking? So these are questions that we have. And now I'm going to hand over to Michael, and we're going to look at wastewater.
Yeah, thank you. All right, let's see if I might just grab the microphone. Can you hear me? Yeah, perfect. So let's take it a little bit in a different direction, because I want to also give you now what we do, a little bit of background, but then the vision. Okay, where we're going. Because I mean, we can talk a lot about the past, but we also want to focus what is the future. Okay, so as first of all, a little bit about wastewater, because it's important. You saw that map from the Patuxent River. There's a lot of what we call point sources of treated water. By the way, the engineers don't call it anymore wastewater treatment plants. They're water resource recovery facilities. Just to put a little bit of a positive spin at this. So here's one example. This is not from the Patuxent, it's from the Eastern Shore, but a newer one. You probably have seen it if you never visited a wastewater treatment plant. They're quite interesting facilities because there's a lot of different, what we call trains, treatment trains that do different things at different time. First of all, they take a lot of those big material out, and they have an aeration system. If you have a modern septic system, you know that you're adding air, you're adding oxygen into the system. That's why it's an active system. Oxygen is fantastic in oxidizing material. So that's what that name comes from. So that's why they do it with a lot of help of pretty incredibly active bacteria. But let's look at what we find in the river. This is now a little bit going north. This is Anne Arundel County. That's the Patapsco River sampling. We did that because we wanted to look at the sewer system versus septic system. But this is a different scenario because I'm still talking about treated effluent. So if I can orient you, these are just numbers going from inside the Patapsco River to the estuarine system into the bay. And close to PT1 is actually the Patapsco River treatment plant outflow. And as you can see, who drinks coffee in the morning here? I think everybody, right? All right, just still even in the evening. So you're adding, actually, you're doing me a big favor because you're putting a fantastic tracer into wastewater, which is caffeine. Caffeine is beautiful because it's degradable, but not super quickly. So when you find it at high concentration, you know there is a source of this material somewhere, and it's typically wastewater or septic, whatever, where it comes from. In this case, I was surprised to see that high concentration. Sucralose, anybody knows what that is? Anybody knows what's Splenda? Splenda, yeah, it's splendid, isn't it? So Splenda, but this is an interesting compound. It's a food additive and it's regulated as such. So there's no regulation how much can be in a wastewater. By the way, none of the micropollutants are regulated, what you can discharge on a wastewater treatment plant. So sucralose is incredibly sweet. That's why we use it as an artificial sweetener, but it's an organochlorine compound. That's 3 chlorine atoms. So when you hear the organochlorine story, it doesn't necessarily need to be toxic in the first place. But we don't really know what it does in the environment. We can measure it very, very high concentration. And that's what we did. Point of this slide is that we have stuff in there which is pretty high, but we found also some compounds which shouldn't be there. It's not in this graph, but there's anybody knows what acetaminophen is? Paracetamol. That's a painkiller. This is actually really well degraded in a wastewater treatment plant if it is working very well. So if it's not working very well, then actually you find it in the wastewater. That's what we did. So we actually basically discovered that that treatment plant wasn't working very well. And then we figured out that other people have noticed that too, and they were suing the treatment plants. We stumbled across it just taking samples across the top. So that gives you a little bit of a sense what it means when you go out, take samples, and look at those wastewater tracers. Here's a little bit of a satellite of basically the middle part of the Patuxent River now. And you see a few of those treatment plants, and you see some of them scattered quite closely. This is more also a bit of an environmental justice issue because they're actually scattered around along mobile homes at times, very small ones. And we know for the fact that some of those really small treatment plants are not performing very well. So I did take samples in my career at Blue Plains at the Potomac River. It treats an incredible amount of water, but it does such an amazing job. It's one of the most advanced treatment plants in the world. It treats the water to an incredible level, and you can see it. When you take a sample, look at all the organics, and you can see it. There's still stuff in there, but it is not even comparable to those effluents from those treatment plants. By the way, anybody knows at the base flow how much water of the Potomac is coming from the Blue Plains treatment plant? Any guessing? 10%. You can imagine how much water that is from one point source. Anyway, so we want to look at this in the future. We're getting it there. We already started taking samples. So we want to be getting a little bit better understanding of our sources and what the actual ecosystem, Patuxent River and different ecosystem within, what they actually do. Are they mitigating the problem? Are they degrading those chemicals? I'm sure they do, but we don't know if it's a wetland better than an oxygenated system and so forth. So there's a lot to be learned of what the river is doing on its own. Can we create, with knowing this, can we basically add benefits to specific implementation of bioremediation and or renaturation of systems? Let's look at septic now. Septic system, who has a septic system at home?
I have two.
Okay, you cut for two then. So you see that's I would say at least half, and they work pretty well because you know you don't smell your wastewater you're discharging if it's a working septic system, but they're designed that they have a leach field and then it goes away. Away means something interesting here because it goes into the groundwater and actually goes into the shallow groundwater. The soil bacteria are supposed to work, and they do. If you give them a little bit more oxygen, they work actually faster. That's why the best available technology septics work so much better and have a removal efficiency of up to 90% of nitrogen, organic nitrogen. In a normal septic system, like I do have at home as well, it's about 20%, so big differences. But there's something which I'm quite concerned is this kind of connectivity. And it may not be that the groundwater always flows away from your well either. So there's always that potential if you don't have a really deep well, if you have a well as well, that you're actually on your own contaminating groundwater. That's why you always should test your well water as well, especially when you're on a shallow well. So we did some work in that realm. One was at Benedict, so a beautiful little settlement at the Patuxent River. They really were thinking about from the county, what can we do? Every single house at Benedict is on septics. So they wanted to know what is the best, are these septics the source of pollutants to the Patuxent River? That was really the question. And if so, what can we do to mitigate the issue? So we dug some wells. Andrew is an expert at wells. I'm not, so he really put them in with my help. But we went out there and had about 6 feet down, maybe 6 feet down wells, and that some shallow groundwater. And sure enough, we found wastewater tracers in those groundwaters. So that's really water which is directly connected to the Patuxent River because it flows straight to the Patuxent River. It's slowed down, but it is flowing down there. And this is an interesting graph because what it really shows is these are just the number of wells, but you can see there's these transects. So this is from a little bit higher and then down the slope, which until we reach the Patuxent River, and you can see kind of a gradient. But you also can see that the wells are really strongly correlated of the caffeine in there, which is coming from the septics and total dissolved nitrogen. So now we have direct proof that the nitrogen loading in those shallow groundwater is directly correlated to the septic system effluent. Because there's always that debate, yeah, but where does that nitrogen come from? It's not the wastewater, it's the birds pooping into the river and so forth, right? But in this case, we had direct proof that the actually septic system contributing to the actual nitrogen loading. And with that, it is the big part of total maximum daily loads and all those regulations coming online. So Benedict is moving ahead with mitigating the problem. Let's come home into local regions. Calvert County. Is everybody here living in Calvert County? Some people in Maryland, in St. Mary's County over there. So Calvert County is a reasonably small county. It's not quite 100,000 people living in Calvert County. It has quite a few first order streams. And first of all, some of the streams actually dry up in summer and some do not. That's kind of an interesting twist in the story. Why wouldn't some of the primary streams dry up? Could be that there's a constant groundwater source, and there is. We did some work on those primary first order streams, and sure enough, we had some streams which we chose which has different density of septics in them in their catchment, because we want to know, okay, the density of septics in the catchment area should directly relate to what we find in the water. That was the hypothesis. This is now our different, don't worry about the site names, because I don't want you to exactly know where the sites are, but I can show you. But what you can see is that our tracer, in this case, Splenda, sucralose, and the total dissolved nitrogen is a really, really close correlation, which was surprising to me because sucralose is so stable that you would find it even after years, and that means the nitrogen would not be correlated. That means this material, that nitrogen, is actually pretty fresh coming out and is directly correlated to our sucralose, which means there is the source here again is pretty convincingly coming from septic system. Not sure how familiar are you with concentrations? It's always a little iffy, right? When they're talking about what milligrams per liter, nanograms per liter, what does that really mean? 7 milligrams per liter is actually a really, really big number for streams. Okay, so just keep that in mind. So these are not slightly contaminated streams in terms of nitrogen loading. If you would taste that water, which I do not recommend to do, it would taste sweet because you have also about 15 micrograms per liter sucralose in it. So just as a little bit of information. So our streams are not doing very well in Calvert County. They're heavily impacted by contamination of our shallow groundwater. That doesn't mean it's not necessarily a huge source of nitrogen to the big, because the flow of those streams is pretty small, but there are really truly impaired systems. So they could do much better if we mitigate the problem. So let's shift to where we are going here at CBL. And by the way, it wasn't Andrew and myself who came up with that name. That was actually Karis. So so she wanted to have an ACE name, and why not call it ACES, right? So that's where this name comes from. So this is the Center for the Study of Anthropogenic Changes in Estuarine Systems. And that was because of a huge donation to CBL, transformative science can now happen. And I want to give the vision. We just got new instrumentation in high-end mass spectrometry, which we put to work as we speak. So this is the vision for what we are going to do. So basically develop new methods for quantifying emerging contaminants. So what does that mean? We want to mitigate. You can only give guidance to change when you know what's going on, right? So, and scientists are there to find information and put it in the right context. And it's really not all that bad. The bay has been pretty steady in terms of contamination, even though the population has been growing. Even maintaining the steady state is a really big achievement. It doesn't feel like it because it's not really improving like we all want, but keeping it there where it is, it's quite remarkable because of such a big push in terms of population growth. But what we really want to do is driving that ship a little bit further. And here are the lists, the preliminary lists, but we're actually in constant dialogue with MDE and DNR, our state agencies we work with, to assist what kind of compounds we're looking for. So one, Andrew already mentioned car tire rubber compounds. I'll have a little story for you after this list, because I think it's a remarkable, interesting story, also a positive story. So these are two compounds, especially that 6-PBD-quinone. Chemists love acronyms like everybody else because they're so long names, you can't even pronounce that thing anymore, so we just use acronyms. Pharmaceuticals, there are a bunch of other, we can already measure quite a few of those. Talked about painkillers and so forth. We had those artificial sweeteners, but this is another list of actually antibiotics. You probably know they're interesting compounds because they actually do impact the environment. They're made to do that. They're antimicrobial agents, antibiotics, pesticides. There's some continuously used pesticides, which are actually also cumulative. So we're going to look at some new compounds there too. We have some interesting cleaning agents. So these are what we call surfactants. or special soaps. So these are not the soap in your soap bar, but they're probably in the, oh, now everybody's awake, thank you. In maybe dishwashing detergents and so forth. So they're interesting one. This particular one is naphthalene sulfonic acid. It's an industrial one. I'm personally very interested in it because naphthalene itself, not the sulfonated version, is actually a pH. And it's really toxic. I remember a little story from New Zealand where I did my PhD and I worked in an aluminum smelter, and it was established in the 60s. They were talking about it was raining naphthalene because of the process they had. So glad I didn't work there when they started doing it, because they did a great job cleaning that up. Flame retardants, you might have heard over the years, those brominated flame retardants became big in the news maybe 10 years, 15 years ago, but there's still quite a few around, which continues to be problematic. So we're going to look at those. And then, of course, PFAS, perfluorinated compounds. They're called forever chemicals, but they're actually, the microbiologists I work with, they always retrain me, said nothing is forever in the microbial world. Some people have already actually figured out specific bacteria can break them down, but you need to have very specific conditions. So there's research done on the microbial world as well. But Andrew mentioned there last I've heard, I think there are 7,000 or 8,000 compounds now known, number growing. So we want to definitely understand it a little bit better and at least evaluate what these compounds do in our local environment. And then, of course, we're open for some ideas. So now here's the story. Anybody knows about the story about coho salmon dying in Washington State? Anybody heard about it? Okay, so there was about maybe 15 years ago, roughly, they had a huge issue. Let's say we are now in Washington State, we have a stream where the coho salmon comes up for spawning, and every time it rains, the coho dies. Acute toxicity, incredibly effective, but very specific to coho salmon. So what happened, it triggered investigation, what is going on, because not other fish were not affected, at least not to that level. So they actually got together with a very capable analytical lab, and they worked with the DNR version in Washington State to figure this out. So what they could nail it down to a quite incredible forensic work, that it's that the runoff from the streets, if it gets quickly into the streams, is the most problematic. So they're related to something in the runoff from streets going to trigger that acute toxicity. That was the first, that's what I started with, not more than that. We're not looking for a specific compound. And then the chemists got to work. And that's quite a pipeline. So what they actually did was they were tracing the toxicity. They were fractionating all the organics in different ways. We can do it. We can do the same thing. And then looked in what kind of fraction is the toxicity. Then they did fractionate it in a different way. And they looked in what fraction is the toxicity. So narrowing it down step by step by step to the point that the final separation, now we're talking about pretty sophisticated chromatography, was then used to really nail down that last fraction so that they could isolate enough material to do some advanced chemical characterization, which you only can do if you almost have a pure compound. That's where they could determine the structure. And that's what this 6-PBD quinone is. It's actually not, so the interesting part is, it's not a direct compound coming from the tires. It's a degradation product of a tire compound. So try to figure that out without doing this kind of forensic work is absolutely impossible. But it took 12 years. So it's a long process, but they got there. Their mitigation process is working. So what they basically said, okay, the way to do it, it's acute toxic, but it's also labile. We only have to slow it down, and then the bacteria degrades. That's not toxic anymore. So what they did, they basically put bioremediation systems in, and they're still working on to slow the runoff from the rivers, from the streets down, so to the point that it can be a little bit more degraded, so that the runoff actually what hits the streams has much less contamination of this particular quinone, so that the coho salmon is not anymore dying from acute toxicity. So I call this a forensic masterpiece, but also that work was needed to have a strategy to really do impactful mitigation processes. So it's not just an analytical success story, but also an environmental success story. And we want to look at these compounds as well, but also more than that, because we want to understand that street runoff a little bit better. Anybody paid attention to when the bay is not doing well? Is it in a dry year or in a wet year? Anytime we have a dry year, it actually does a lot better. So now you can put two things together. You know that runoff is one of the biggest problems we have. It's combined, of course, we can talk about wastewater overflows when you have a combined sewer system, because you have to bypass it at big storm events and so forth. But big rains, big storm events, and a wet year is bad news for the bay in generally speaking, in terms of the contaminant and nutrient load. So that's in a way, it's not really good news with the forecasting of extreme events increasing as well. But this triggers really a more in detailed characterization of runoff. I think is needed so that we understand this material and what gets into our water system a little bit better. And that's basically it. So I'll open up the floor to some questions.